Hello, my name is Matt Smith with Shunk USA. I'm Senior Applications Engineer and work with magnetic gripping systems. Today I'll be talking with you about how magnets work. We'll be looking at three typical types of magnets that are in the industry today, how they work, and what the advantages of them are. We'll also talk about how magnets are used in automation and what things to look for if you consider using magnets. To start with, I'd like to describe a basic magnetic circuit. This circuit is similar to a horseshoe magnet that you may have had as a child. You have a north and a south pole, and when you connect it to a workpiece, it completes the circuit and creates some magnetic attraction. We use this to our advantage to help pick and place parts. Magnetic gripping depends a lot on the type of workpiece. We have different types of magnets that work better with different types of material. In general, it needs to be ferrous steel type of material that we can pick up, but the thickness and consistency make a big difference. In this slide, you see that we have a given magnet. It's a bipole magnet with a north and a south, and we have two different workpieces. One is thick and the other is thin. You can see that the magnetic flux pattern goes very deeply into the thick piece, and we're able to utilize the magnetic flux completely. Whereas on the thinner part, you can see that much of the magnetic flux is going into space and is unused. Therefore, we're only able to capture the part with a fraction of the amount of flux that we would normally do with a big piece. So that's okay. We can size the magnet differently for the thin parts than we would for the thick parts. And you might ask, why would you not just use a magnet that has short poles and short flux bands for everything? Well, the reason is because if we have thicker material, we want to use as much as we can. We can get more lifting force with the similar sized magnet. The three types of magnets in the industry are categorized into electromagnets, permanent magnets, and permanent electromagnets. Electromagnets are the type of magnet that you might see in a high school lab, for instance, or in automation they're used sometimes for very lightweight parts. These magnets require current to operate at all times. So as soon as the current is cut off, then the magnet will release the part. That's an advantage. You can operate very quickly, but it's also a disadvantage because if the power is interrupted, you will lose the part. The next type is the mechanical or permanent magnet. These type of magnets are what people call rare earth magnets. Sometimes we play with those. They're very powerful magnets that don't have an on and off button. So what we would do with these is work with the mechanical portion of the housing to slide the magnet either away from the part or towards the part to engage the part. The advantage of these is they're very simple in design. They're usually fairly inexpensive. The disadvantage is that they have very low holding force and they are bulky. So the power to weight ratio of these magnets is very low. The third type is the permanent electromagnets by Shunk. These magnets combine the best of both worlds. So it's electro in that we use electricity to shift the magnet from inactive to active and then back again from active to inactive, but it still has the same holding force as a permanent magnet. Now the difference between an electromagnet and a permanent electromagnet is that the permanent electromagnets from Shunk only require a pulse of electricity to activate. So after 300 millisecond pulse of electricity, the magnet is changed, and then you could literally disconnect the cable and it will hold that part permanently until you change it back. The advantage of that is that it's a safe magnet so that it will not drop parts until you instruct it to do so. Electromagnets typically have a coil that surrounds a part of the magnet, and when electrical current is passed through this coil, it creates a magnetic flux pattern. You apply this to the part, and then you can pick and then place the part, disconnect the power, and release the part. The disadvantage is that these require an enormous amount of power, so they're very inefficient, requiring power at all times. The bigger the magnet you have, the more power it requires, and it's very costly to operate. Another disadvantage is that they are not safe. They will drop parts. If the power is interrupted, they will drop the part. And another disadvantage is because they consume so much power, they also generate a lot of heat. So you get heat, and in some cases with bigger magnets, you would have to have some type of a heat transfer unit to get rid of it. These are the type of magnets that have given the magnetic industry sort of a bad reputation. They do create a high residual Gauss, residual magnetism, in other words, in the part, and some other type of magnets don't do that as much, but these are pretty bad about that. If the parts are unaffected by that, or you're going to go through a heat treat process afterwards, then that might not be a problem. Permanent magnets are either a sliding magnet inside of a tube, or there's other magnets on the market that can shift the poles. So you see on the left side screen, where the colored arrow is, you see the North Pole on the top and the North Pole on the bottom are aligned. And this creates a magnetic flux pattern that's within the body of the gripper. When you shift that top magnet and rotate it 180 degrees, now you see that the poles are misaligned. So the south and the north are aligned together. And this creates a different flux pattern, and now the flux pattern will exit the magnet at the face of the magnet, and you can grip the part. With permanent electromagnets, we use a combination of both. We still have two types of magnets, or now we have two types of magnets. The main magnet on the bottom of both of these slides is a permanent magnet, rare earth magnet, and then the one on the top is changeable. So this magnet can be changed in its polarity from north to south, back to south to north, by simply running an electrical current across it. So we have come up with technology that allows us to do this very simply. So with a pulse of electricity, just 300 milliseconds, it allows us to change the polarity of one magnet so that the poles align or misalign, and either activate or deactivate the magnet depending on what we want. This is an advantage to many applications because now we have a magnet that's very power dense. It has a very high power to weight ratio. These are very compact magnets for their size. They also react very quickly, and they're a very safe magnet that prevents dropping. In addition to that, they're very efficient. The magnetic current required is very low and does not require, does not generate a lot of heat. Magnetic gripping is very similar to parallel gripping in that it requires friction to hold the part. You can see on the left we have a parallel gripper with two jaws, and we're depending on friction from preventing the part from slipping from between the fingers from gravity. So the higher the force, the more grip you would have, but we're still depending on that coefficient of friction. Magnetic gripping is very similar to parallel gripping in that we have a force being applied to the part and holding it to the surface of the magnet, and that's the magnetic flux. So you can see it's a very similar theory in how we grip with magnets when compared to parallel gripping. So when you have applications that you're thinking about doing, think about that. Could it be handled with a parallel gripper, or what would it be like if we had this invisible jaw holding the part from one side? I'd like to make you aware of air gap. Magnets have their best performance when they are touching the surface very completely. The ideal situation is to have a soft, like cold rolled or hot rolled steel that's been machined and ground. The surface of the magnet is also ground, and in this case, you have perfect surface-to-surface contact. In a case like that, we can depend on the magnet to give its full performance. If there's anything that prevents it from having full surface contact, then that takes away from the performance of the magnet. This could include rough surface from milling and machining. It can include epoxy or paints. It can also include rust and mill scale. Any of these things that are on the part we need to know about. And again, this doesn't mean that we can't handle it with a magnet, but what it does mean is that if a normal magnet could pick up 10 kilograms, it might only be able to pick up 5 now. So we'd use 2 to get the full holding force of 10 kilogram that we might need. And you can see the grip force chart or graph. In this graph, it shows the thickness of material and the performance of the magnet on one axis, on both axes. So with the introduction of as little as a ½ millimeter of air gap, we've lost over 70% of our grip force. So just keep this in mind when magnetic applications come up, that if there is an air gap, we do need to know about it, and we can help you walk through the process to select the right magnet. These are some examples of applications done here in the USA. Applications with customers just like you that may have had handling issues with any other type of handling, but magnets were a good choice. In the upper left, we see a FANUC robot with a large end effector. This customer is using a plasma torch to cut out these triangular shaped pieces, and because they're so close together, it was difficult for them to pick up with a parallel gripper. Also, because they're roughly triangular or maybe trapezoidal in shape, it was difficult to grip them with a gripper in the right location. It turns out a magnet was an ideal tool for this. We developed a customized magnet end of arm tool that expands and retracts depending on the size and the number of pieces they pick up, and it gives them the ability to pick in place at a very rapid rate. The top middle picture is from another customer. This application was picking and placing C-channel iron. Now, as you may know, these C-channels are shipped to the customer with one piece will have the leg up, and then the other piece would have the leg down. So we need to be able to pick up, rotate one around so that they all have legs up. The customer was able to create this end of arm tool using 4 shunt magnets and was able to pick, rotate, flip the parts, and then handle them into a manufacturing process where they were cut into the pieces that they needed. The upper right is a magnet that we design that we have come up with for a customer. The customer is handling round bar stock, and they're using this for machine tending. The robot would be loading a chuck, and then the bar stock would be milled down and then picked from the chuck, and a new piece is placed in place of the old piece. So in this case, we have 2 magnets on one end effector. One magnet would pick the finished piece, and the other magnet's holding the unfinished piece and would insert that into the chuck, and then the process starts over again. The lower left is an application where a customer had very thin pieces that needed to be transferred from one location to another. So we have an end effector that has multiple magnets on it and is holding a sheet metal piece to be lifted and then transferred over, handed off to another end of arm tool, and then lowered again. So the challenge this customer had is that they needed to have a magnet that could grip thin pieces and not pick up another one beneath it. We used the smaller shunt magnet for this. It worked very good, and to my knowledge, it's still working to this day. The lower middle shows an application which again was machine tending with much larger steel billets. These were being fed into a chuck, so the workpiece had to be gripped off center. We needed to have a strong enough magnet that would prevent the part from falling off, and also had to hold the workpiece very securely. We were able to develop pole extensions to bolt onto this magnet that mirrored the shape of the part, allowing the part to be very rigid in the jaws as we were carrying it. The final end effector on the lower right is an application with a customer who is handling carts. These carts had to be manipulated and moved from one section or one place to another and stacked. There was no other way for them to pick these but using some type of surface contact They were thinking about using vacuum. The carts were too heavy, and the vacuum end effector would be very large, and it also uses a lot of electricity. So when we approached them about a solution with magnets, they were pleased with that and moved forward with that solution. The magnets in this picture are two of our larger magnets and have 196 kilogram of lifting force each. I want to thank you for watching my presentation today. If you have any questions, please feel free to contact us at the numbers below. We'll be glad to answer any of your questions and look forward to working with you. Thank you very much and have a nice day.